Hello and welcome to this lab lecture on regularization. In this lecture we will work with a dataset that is aiming at predicting the price of some automobile. In this lecture we will focus on the two regularization techniques, lasso regression and ridge regression, and we will apply these techniques to this dataset. And you can see we are varying certain parameters. For example, we are performing model creation for a large range of shrinkage parameters. You can see this lambda value here, and we are trying to find out which model is providing the lowest error. We will take a look at the coefficients of the model, and pretty similar we will work on ridge regression, where we will also find out what the optimum shrinkage parameter is, and we will see how the coefficients are different for ridge regression compared to lasso regression. Alright, stay with me, and now we're coming to the coding section. After you have downloaded and extracted the file from the homepage, you can see these three files are in the folder. Please click on this projects file. Now RStudio is starting, and you can see there is a final file and a template file. We will work on the template file, but you can also see the final result in the regularization underline final file. So please click on the template file, and this is the one that we are working with right now. At the beginning, we are starting with a chapter on data understanding, where we are setting the seed so that you get exactly the same results that I have, and we are loading the packages. GLMnet is holding the model creation. All these lasso and ridge regression models are stored in here, and we will also use dplyr and ggplot for data manipulation and plotting. The dataset we will work with is focusing on automobiles, and our task is to predict the price of an automobile based on several independent variables. We are not going the whole way, we are just creating the models, we are learning about the coefficients, but we're not checking the performance, and we are not creating the predictions in the end. So we are starting by importing the data, and here we will download the data directly from the folder. So if you didn't run this chunk before, there is no subfolder data, and the file was not downloaded. For the very first time, the file will be downloaded. Afterwards, it's only going to be loaded directly. I run all the chunks above, which means I load the packages. And now I run this chunk, which also imports the data and performs some small modifications on the data. So it's just casting the columns to numeric to make it possible to work with it. And then we are using not all of the variables in this lecture. We are only focusing on the numerical columns. So we filter for these. And we can take a look at the summary of cars filled. Run this, and you can see all the columns are numeric, and also there is no missing data in this data set. So that's good, we can move forward. You can see that the dataset is really small. It's only having 205 observations. So we're not splitting the data extensively. Instead, we will assign all data to train, and we will use cross-validation in the modeling part. Because now we are starting with the modeling, and we are starting with lasso regression. And in here, we have to separate the independent variables from the dependent variables. You will see what I mean in a second. We will create an object called trainX. And for this specific technique, we need to modify the data slightly. we need to make it to a model matrix which takes the formula into account. So the dependent variable is price and all the other columns are taken into account. And we will use the train dataset. And of the resulting model matrix, we will use all columns except the last one. And the target variable we can directly take from the variable price within the train dataset. And we will also specify the range for the shrinkage parameter. The shrinkage parameter covers the range from 0.01 to 1000, and this is what we are doing with this line. And now we are ready to create the model. We will call the model lasso, and from the package glmnet we will use the function cv glmnet, which performs the k-fold cross-validation for the glmnet model creation. And now we can pass several parameters. The first one is the x parameter, which is our train x. Then we have the target variable, which is going to be train y. And the next one is going to be the family. That has to be Gaussian. Then we want to perform lasso regression, and we check by clicking F1 what the parameter for lasso is. And there is a specific parameter. Yeah, actually you have to check the help for glmnet rather than cv glmnet, because the parameter we are searching for is described in this function, which is not adding the stuff on cross-validation. And here you can see the alpha parameter. So here you can see the description, the ElasticNet mixing parameter, which has a range from 0 to 1. And here you can see it, alpha equals 1 is the lasso penalty, alpha equals 0 is the ridge penalty. So this is what we are going to use right now. So this is going to be the next parameter in our model creation. Alpha equals 1. And we want to perform it for a complete range of lambdas. So lambda equals lambdas. And since it is cross-validation, we need to specify the parameter n folds, and we follow the classical 10-fold cross-validation. Let's run the complete chunk. Alright. Yeah, of course, there's a typo. It has to be sequence. Let's try it again. Alright. So that seems to work. And now we can create a plot of this. Plot model lasso. We want to see the labels, and the x variable shall be lambda. Alright. What you can see here is the mean squared error versus the lambda. The graph is showing the lambda in the log format, but that's not too important to us right now. You know, the very small lambdas, which are starting at 0.01, are at the left, and the large ones, like 1000, are at the right. And you can see how the error of the models is changing with the different shrinkage parameters. You can see we have a certain error at the beginning, and then we are decreasing once we reach some final point. And then from there on, if the shrinkage parameter is further increased, the overall model error is increased. And what we are looking for is the shrinkage parameter that has the minimum error. And this is what we're going to find out right now. So we want to find the optimum lambda and call the object lambda opt. And this is stored in our created object, model lasso. And here you can find lambda min. And also can take a look at it. Lambda opt is 0.79. And we can also get the coefficients. Let's store the coefficients in the object lasso qf. For this we will use the predict function, pass our lasso object, and we want to see the results for the optimum lambda. We need to specify another parameter, new x, that is going to be our validation data, val x. And very important, the type has to be coefficients. And we also want to see the results. You can see that there are certain parameters that are even set to 0. So these are to be seen with the dots. And this is one of the core feature of lasso regression. That it's possible that certain variables are not taken into account at all anymore. And we can also find out how the parameters are changing with the shrinkage value. So let's see how this works. So we add a new chunk in here, and we will need to create a new lasso object, which we will call model lasso single. And we will call the function glmnet, where we pass for the x parameter train x, for the y parameter train y, family has to be Gaussian again. It's all pretty similar to what we did before, except that we're not creating a cross-validation model right now. Okay, alpha equals 1 for lasso regression, and the lambda values need to be the lambdas. That worked. And now we can create a plot of this object, model lasso single, label will be set to true, and important now is to set the x variable, which is going to be lambda. And here you can see it. We can see the complete range of lambdas from very small to very large. And you can see for all the variables that we have in our dataset how their model coefficient is changing with lambda. And you can see they are all maximum for lambdas very close to 0, and the more lambda is increased, the smaller the coefficients get. And that's the whole idea of regularization. But this is showing it very nicely in one single plot. Okay, now we come to the ridge regression, and we create an object called model ridge. Again, we will use CV glmnet and the same data, train x as the x variable. The target variable is going to be train y. Family is Gaussian. And we have seen the alpha parameter. For ridge regression, it has to be 0. The rest is similar. Lambda equals to lambdas. So we pass all our lambdas to the parameter lambda. And since it is cross-validation, we will set a parameter for the number of folds. And that's it. It's that easy to create our rich regression model. Now we can create the plot. Model rich. Label equals true. And we will again show the lambdas. And here we can see again a similar plot to what we had before. We can see the mean squared error of the models for different shrinkage parameters. And the next point is to find the shrinkage parameter that leads to the lowest overall model error. And that's very similar to what we did before. Lambda opt will be model rich $lambda min. And we can also plot this and run the complete chunk. Alright. And if we also want to get the coefficients, we can do so and create an object called richCoef, where we use the predict function and pass our model rich, and we specify the shrinkage parameter to be lambda opt. New x is going to be our validation data x, and the type is going to be coefficients. And of course we also want to see them. And here you can see all the parameters are still part of the model. None of them is going to be 0, but they are drastically reduced. Alright, that's it for this lecture on regularization. Thank you very much and see you in the next one.